Every day, billions of people rely on a vast engineering system they rarely see. Hidden beneath roads, neighborhoods, farms, rivers, and cities lies one of the largest energy transportation networks ever built, the natural gas pipeline network. Stretching for millions of miles across continents, it quietly delivers energy to homes, hospitals, schools, factories, power stations, and industries around the clock. Unlike highways or power lines, most of this infrastructure remains completely invisible, buried safely underground. Yet modern civilization depends on it every hour of every day. Before we can understand how hydrogen may transform our energy future, we first need to understand the extraordinary pipeline system that has powered economies for decades. Transporting enormous amounts of energy by truck, rail, or ship would be expensive, inefficient, and impractical for continuous supply. Pipelines solve this challenge by creating a permanent energy highway that moves gas safely over hundreds or even thousands of miles. Once compressed and flowing, natural gas travels continuously with very little interruption, providing industries and communities with dependable energy 24 hours a day. Compressor stations positioned along the route maintain pressure and keep the gas moving. This hidden transportation system has become one of the most efficient methods ever developed for delivering energy at national scale. Hydrogen may also travel through pipelines, but it behaves very differently from natural gas. Natural gas is primarily methane, a relatively large and stable molecule. Hydrogen, by comparison, is the smallest molecule in the universe. Because of its tiny size, hydrogen moves faster, diffuses more easily, and interacts with pipeline materials in ways that methane never does. These differences create entirely new engineering challenges. A pipeline designed to transport methane cannot automatically transport hydrogen without careful evaluation. Understanding these molecular differences is the first step toward building a reliable hydrogen infrastructure. Looking inside the pipeline reveals why engineers pay so much attention to molecular behavior. Methane molecules are larger and move differently through steel pipelines, while hydrogen molecules are extremely small and far more mobile. Their size allows them to penetrate tiny imperfections within metals and seals, increasing the importance of material selection, welding quality, pressure management, and leak prevention. This microscopic difference has enormous consequences for large-scale infrastructure. What appears to be a simple pipeline from the outside becomes a highly engineered system where chemistry, materials, science, and mechanical engineering all work together. Once the gas enters the transmission network, the journey continues across vast distances toward the people and industries that depend on it. Large transmission pipelines branch into regional distribution systems before finally reaching neighborhoods, commercial buildings, manufacturing plants, and power stations. Every junction, valve, regulator, and monitoring station has been carefully engineered to maintain safe operation while delivering energy exactly where it is needed. This hidden network operates continuously beneath our feet, forming the backbone of modern energy distribution. As hydrogen begins entering these systems, engineers must determine how this remarkable infrastructure can evolve to support the next generation of clean energy. One of the greatest strengths of pipeline infrastructure is its reliability. Unlike trucks or rail cars that operate on schedules, pipelines move energy continuously, 24 hours a day, regardless of traffic or most weather conditions. Advanced monitoring systems constantly measure pressure, temperature, and flow rates to ensure the network remains stable. Every section of pipe is designed to withstand decades of operation under demanding conditions. This dependable performance is one reason pipelines became the backbone of national energy systems. As hydrogen enters these networks, maintaining the same level of reliability becomes an even greater engineering challenge, requiring new materials, monitoring technologies, and operational strategies. The journey of natural gas does not end at the transmission pipeline. As the gas approaches populated areas, the network divides into smaller distribution pipelines that deliver energy directly to homes, businesses, hospitals, schools, and commercial buildings. Pressure is carefully managed throughout this journey, ensuring that every customer receives a safe and consistent supply. Although this entire system operates underground, it powers daily activities that most people take for granted, from heating homes in winter to cooking meals and producing hot water. It is a remarkable example of hidden infrastructure quietly supporting modern life. Before natural gas enters a building, it passes through several engineered safety systems. Pressure regulators reduce the high transmission pressure to levels suitable for residential or commercial use. Meters accurately measure consumption, while isolation valves allow sections of the system to be shut off for maintenance or emergencies. Every connection has been carefully designed to balance safety, efficiency, and reliability. If hydrogen is introduced into these distribution systems, many of these components may require upgrades or redesigns to accommodate hydrogen's unique physical properties while maintaining the same high standards of safety. Building a hydrogen pipeline network is not simply a matter of replacing methane with hydrogen. It requires an entirely new layer of supporting infrastructure. Production plants, storage facilities, compressor stations, purification systems, monitoring equipment, and distribution hubs must all work together as a coordinated network. Engineers must determine where existing natural gas infrastructure can be adapted and where completely new facilities are needed. This planning process involves balancing technical performance, economics, safety, and long-term energy demand. Every successful hydrogen economy begins with carefully designed infrastructure rather than individual pieces of equipment. Every long-distance pipeline depends on compressor stations to keep the gas moving. As gas travels through hundreds of miles of pipe, friction gradually reduces its pressure. Compressor stations restore that pressure, allowing the gas to continue its journey efficiently. For hydrogen, compression becomes even more critical because hydrogen has a much lower energy density by volume than natural gas. Moving large quantities of hydrogen often requires higher flow rates and specialized compressor designs capable of handling its unique molecular characteristics. These facilities are among the most important and least visible machines within the entire pipeline network, quietly ensuring that energy continues flowing across countries and into the communities that depend on it. While pipelines, valves, and compressors perform the physical work, an invisible digital system constantly monitors every part of the network. This system is known as SCADA, or Supervisory Control and Data Acquisition. Thousands of sensors installed throughout the pipeline continuously transmit information on pressure, temperature, flow rate, valve positions, and equipment status back to centralized control rooms. Operators can immediately detect abnormal conditions, isolate sections of the network, and optimize gas flow without physically visiting each location. For hydrogen pipelines, this digital intelligence becomes even more important, providing continuous situational awareness and enabling rapid response to maintain safe and reliable operation. A successful hydrogen economy requires far more than individual pipelines. It demands an integrated network connecting hydrogen production facilities, storage sites, compressor stations, industrial users, ports, power plants, and future fueling infrastructure. Each connection must be carefully engineered to ensure hydrogen moves efficiently from where it is produced to where it is consumed. Engineers analyze demand patterns, transportation distances, pressure requirements, and future expansion plans before determining where each pipeline should be built. Producing hydrogen and consuming hydrogen rarely happen at exactly the same time. One of the most effective solutions is underground storage. Engineers use naturally occurring salt caverns, depleted natural gas reservoirs, or specially designed geological formations capable of safely containing enormous volumes of compressed hydrogen. These hidden storage systems act like giant energy reservoirs, preserving renewable energy for future demand while helping stabilize the entire hydrogen economy. Every kilogram of hydrogen flowing through a pipeline represents valuable energy. Metering stations continuously measure flow rate, pressure, temperature, and gas composition to determine exactly how much hydrogen is entering or leaving each section of the network. These measurements support commercial transactions, operational planning, and system balancing, while providing operators with accurate real-time information across the pipeline. No pipeline system can be considered safe without the ability to isolate individual sections. Isolation valve stations allow operators to quickly stop the flow into a specific segment during maintenance or emergencies without shutting down the entire network. These massive steel valves are strategically positioned along the pipeline and serve as one of the most important safety barriers protecting critical energy infrastructure. Transmission pipelines operate at extremely high pressures, but those pressures cannot be delivered directly into local distribution systems. Pressure reduction stations use precision regulators, relief valves, and automated controls to safely lower pressure while maintaining stable flow. For hydrogen, managing pressure becomes even more important because of its unique physical behavior and its interaction with pipeline materials. Instead of excavating pipelines for inspection, engineers use intelligent devices known as pipeline pigs. These machines travel inside the pipeline while it remains in service, cleaning internal surfaces and collecting detailed inspection data. Modern smart pigs detect corrosion, cracks, dents, wall thinning, and other defects long before they become serious problems, helping operators extend pipeline life while improving safety and reducing maintenance costs. Modern leak detection combines pressure sensors, fiber optic monitoring, acoustic sensing, and artificial intelligence. Digital systems continuously compare real operating conditions against expected performance, allowing operators to detect even small abnormalities. Because hydrogen molecules are much smaller than methane molecules, advanced monitoring technologies will become one of the most important safety systems within future hydrogen pipeline networks. One practical way to begin the hydrogen transition is by blending hydrogen into existing natural gas pipelines. Specialized blending stations precisely control the amount of hydrogen entering the gas stream, using flow meters, automated valves, and continuous monitoring equipment. Although blending is only a transitional solution, it allows existing infrastructure to support lower carbon energy, while engineers continue developing dedicated hydrogen networks. Ultimately, many regions will require pipelines specifically designed for hydrogen service. Dedicated hydrogen pipelines incorporate specialized steels, advanced coatings, hydrogen-compatible seals, optimized compressors, and enhanced monitoring systems designed to handle hydrogen safely and efficiently. These pipelines represent the long-term foundation of a global hydrogen economy. Europe is transforming hydrogen from concept into reality through the European hydrogen backbone. Existing natural gas pipelines are being evaluated for conversion, while new hydrogen pipelines are planned to connect renewable production with industrial centers, ports, and power plants. The objective is to create one of the world's largest interconnected hydrogen transportation systems spanning multiple countries. The United States is pursuing regional hydrogen corridors that connect production facilities with nearby industrial users, transportation hubs, and storage sites. As these regional networks expand and eventually interconnect, they could evolve into a nationwide hydrogen transportation system supporting clean manufacturing, heavy industry, and future energy security. The pipeline of the future will not simply transport hydrogen, it will continuously monitor itself. Artificial intelligence will analyze data from thousands of sensors, while digital twins simulate the entire network in real time. Operators will predict equipment failures, optimize compressor performance, detect abnormalities earlier, and improve reliability before problems ever occur. Looking beyond today's infrastructure, engineers envision an international hydrogen supergrid connecting renewable energy resources across entire continents. Wind farms, solar parks, hydroelectric stations, underground storage, ports, industries, and cities could all become part of one intelligent energy transportation system. Similar to how the internet transformed communication, hydrogen supergrids could transform the movement of clean energy around the world. Throughout this documentary, we've explored far more than pipelines. We've uncovered an entire hidden engineering ecosystem: compressor stations, pressure regulators, intelligent monitoring systems, underground storage, blending facilities, leak detection technologies, and the digital intelligence that keeps everything operating safely. These are the systems quietly supporting the global energy transition, yet they remain largely invisible to most people. If you're curious to go even deeper, explore H2 Hub by Renewable. Discover interactive engineering schematics, industrial equipment libraries, infrastructure databases, engineering calculators, technical resources, and educational tools designed to reveal how hydrogen and industrial energy systems really work. Because solving tomorrow's sustainability challenges begins with understanding the hidden engineering systems that power our world today.